Hello, my dear, and welcome to our astronomy course. Okay, today in our lecture number 11, we are going to start. We are going to start investigate terrestrial planets. So let's start. In preceding lectures, you learned how our solar system forms as a byproduct of the formation of stars. You also saw how distance from the sun determined the general character of each planet. In today's lecture, as you begin to study the individual planets, you can continue comparing the planets with each other, searching for similarities and contrasts. Like people, the terrestrial planets are more alike than they are different. But it is the difference that are most memorable. As you explore, you will be searching for answers to our essential question. What are the main features of Earth when you view it as a planet? How does distance from the sun affect the characteristics of a planet and its atmosphere? How does size determine the geologic activity and evolution of a planet? And what is the evidence that surface conditions on Venus and Mars were originally more like Earth-like than at present? So once you are familiar with the family of a terrestrial planet, you will be ready to meet a stranger group of characters in the next part of our lecture. The birds of outer solar system. If you had been the first person to step onto the surface of the moon, what would you have said? Neil Armstrong responded to the historic significance of the first human step on the surface of another planet. Buzz Aldrin was second, and he responded to the moon itself. It is desolate, and it is magnificent, but it is not unusual. Many planets in the universe probably look like Earth's moon, and astronauts may someday work on such worlds and compare them with Earth's moon. The comparison of one planet with another is called comparative planetology, and it is the best way to analyze the world in our solar system. You can learn much more by comparing planets than you could by studying them separately. If you visit the city of Granada in Spain, for example, you will probably consult a travel guide. And if it is a good guide, it will do more than tell you where to find museums and restaurants. It will tell you to look at the place called the Alhambra and compare it with buildings in Morocco. For example, their similarities reveal the Moorish influence on Spain. And in this lecture, you are going to visit 5 Earth-like worlds And this preliminary section will be your guide to important features and comparisons. Okay? You are about to visit Mercury, Venus, Earth, Earth, Moon, and Mars. It may surprise you that the Moon is on your itinerary. Look at this, right? It is, after all, just a natural satellite orbiting Earth and isn't one of the planets. But the Moon is a fascinating world of its own. It makes a striking comparison with the other worlds on your list. And its history gives you important information about the history of Earth and certainly the other planets. And this figure compares the 5 worlds you are about to start. The first feature you might notice is diameter. The Moon is small and Mercury is not much bigger. Earth and Venus are large and quite similar in size, but Mars is a medium-sized world. You will discover that size is a critical factor in determining a world's personality. Small worlds tend to be geologically inactive, while larger worlds tend to be more active. The terrestrial worlds are made up of rock and metal. They are all differentiated, which means they are each separated into layers of different density, with high density materials on the inside and lower density materials on the outside. As you learned in the previous lectures, when the planets formed, their surfaces were subjected to heavy bombardment by leftover planetesimals and debris in the young solar system. You will see lots of craters on this world, especially in Mercury and the Moon, many of them dating back to the heavy bombardment era. Notice that crater surfaces are flowed. For example, if a lava flow covered up, some craters landscape after the end of the heavy bombardment. Few craters could be formed later on that surface, because most of the debris in the solar system was gone. When you see a smooth plane on a planet, you can guess that the surface is younger than the heavily cratered area. Another important way you can study a planet is by following the energy flow. In the preceding lecture, you learned that the heat in the interior of a planet may be partially from radioactive decay and partially left over from the planet's formation, right? But in any case, it must flow outward toward the cooler surface where it is radiated into space. In the process of flowing outward, the heat can cause a convection current, magnetic fields, plate motions, quakes, faults, volcanoes, mountain building, and more. Heat flowing outward through the cooler crust makes a large world like Earth geologically active. In contrast, the Moon and the Mercury, both small worlds, cool quickly in size, so they have little heat flowing outward now and are relatively inactive. When you look at Mercury and the Moon in this figure, you can see their craters, plains, and mountains clearly. They each have little or no atmosphere to obscure your view. In comparison, the surface of Venus is completely hidden by the cloudy atmosphere, even thicker than Earth. But the medium-sized planet has a relatively thin atmosphere. You might ponder two questions. First, why do some worlds have atmospheres while some do not? You will discover that both size and temperature are important. The second question is more common. Where did those atmospheres come from? To answer that question, you will have to study the geological history of these worlds. Why do you expect the inner planets to be high-density worlds? In the previous lecture, you saw how the inner planets form from hot inner parts of the solar nebula. So ice solidified there, and so the inner planets could grow only from particles of rock and metal able to condense from hot gas. So you expect the inner planets to be made mostly of rock and metal, which are dense materials, right? As you visit the terrestrial planet, you will find craters almost everywhere. What made all of those craters? Earth is the basis for your comparative study of the terrestrial planet. So you should pretend to visit it as if you didn't live here. It is geologically active with a molten interior and heat flowing outward that powers volcanic earthquakes and moving crustal plates. Almost 75% of Earth's surface is covered by liquid water, unlike any other planet in our solar system. And the atmosphere contains a significant amount of oxygen, also unlike any other planet. There is evidence that Earth and the other terrestrial planets, plus Earth's moon, pass through 4 development stages. Let's look at this slightly. The first stage of planetary evolution is differentiation, the separation of material according to density. As you have already learned, Earth is differentiated. It has a dense metallic core, a less dense rocky mantle, and a low density crust. That differentiation is understood to have occurred due to melting of Earth's interior, caused by heat from a combination of radioactive decay, plus, plus energy released by falling matter during the planet's formation. Once the interior of Earth melted, the densest material were able to sink to the core. The second stage, cratering, could not begin until a solid surface formed. The heavy bombardment of the early solar system made craters on Earth just as it did on the Moon and other planets. As the debris in the young solar system cleared away, the rate of cratering impacts fell rapidly to its present low rate. The third stage, flooding, began as radioactive decay continued to heat Earth's interior and caused rock to melt in an upper mountain, where the pressure was lower than in the deeper interior. Some of that molten rock welded up through cracks in the crust and flooded the deeper impact basins. Later, as the environment cooled, water fell as rain and flooded the basins to form the first ocean. Note that on Earth, basin flooding was caused by lava and later by the fourth stage, slow surface evolution, has continued for at least the past 3.5 billion years. The surface is constantly changing as sections of crust slide over and against each other. But push up mountains and shift continents. In addition, moving air and water erode the surface and wear away geological features. Almost all traces of the first billion years of Earth's history have been destroyed by the active crust and erosion. Terrestrial planets pass through their four stages, but differences in mass, temperature, and composition between the planets can emphasize some of those stages over others and produce surprisingly different forms. From what you know of the formation of Earth, you would expect it to have differentiated. But in science, evidence rules. What does the evidence reveal about Earth's interior? Earth's mass divided by its volume tells you its average density, right? And it gives us about 5.5 grams per cubic centimeter. But the density of Earth's rocky crust is only about half that much. So a large part of Earth's interior must be made of material denser than crust rock. So scientists have clear proof that Earth did differentiate. Even though the deepest wells drilled do not even reach to the bottom of the crust. Each time an earthquake occurs, seismic waves travel through the interior and register on seismograph all over the world. Analysis of these waves shows that Earth's interior is divided into a metallic core and a dense rocky mantle. Metallic core with solid, in some parts liquid on the earth, and dense rocky mantle. You can see as a rosy and yellow color. And very, very low density crust. The core has a density of 14 grams per cubic centimeter. Denser than lead. And it's evidently composed of iron and nickel at a temperature of roughly 6,000 Kelvin, or simply centigrade. In this high temperature, we cannot big differences between centigrade and Kelvin. That means the core of Earth is as hot as the surface of the sun. But the high pressure keeps the metal solid near the center of the core and liquid in its outer part. Two kinds of seismic waves show that the outer core is namely liquid. The heat or pressure waves travel like sound waves and can penetrate in liquid. But S waves travel as a type of side-to-side vibration that can't pass through a liquid. Scientists deduce the size of the liquid core by observing where S waves get through Earth's interior and where they don't, as you can see at this figure. The outer boundary of core lies slightly more than halfway between Earth's center and surface. Earth's magnetism gives you further evidence about the core. The presence of a magnetic field is a clue that part of Earth's core must be namely liquid metal. Convection currents steer the liquid and it also rotates as Earth rotates. Because of these motions and because it is a very good conductor of electricity, the liquid outer core generates a magnetic field through the dynamo effect, a different version of the process that creates the sun's magnetic field. From traces of magnetic field retained by rocks that formed long ago, geologists conclude that Earth's magnetic field reverses itself every 700,000 years or so. periodic reversals, though poorly understood, seem to be a characteristic of the dynamo effect. As displayed in geology science, Earth's mantle is a thick layer of dense rock that lies between the molten core and the solid crust. Models based on seismic data indicate the mantle material, so it should be solid, but capable of flowing slowly under pressure, like asphalt used in paving roads, which shatters if struck by a sledgehammer, but bends slightly under the weight of a truck. Are you agree with me? Like, the geologic term for material with those properties is plastic. Just below Earth's crust, where the pressure is less than at great depth, the mantle is more plastic, meaning it flows more easily. Earth's rocky crust is made up of low-density rock, and you can think of it as floating on the mountain. The image of a rock floating may seem odd, but recall that the rock underneath the crust in the mantle is very dense. Also, just below the crust, the mantle rock tends to be most flat. So great sections of low-density crust do indeed float on the mantle like huge lily pads floating on a pond. The crust is thickest under the continent, up to 60 kilometers deep, and thinnest under the oceans, where it's only about 10 kilometers deep or so. Tectonic motions and the erosive action of water makes Earth's crust highly effective, or better say, makes highly active. Look at the active Earth and notice 3 important points plus 6 new tabs. First, the motion of crust plates produces most, but not all, of the geologic activity on Earth. Earthquakes, volcanic, and mountain buildings are usually linked to motions in the crust and the locations of plate boundaries. Second, the continents on Earth's surface have moved and changed significantly over periods of hundreds of millions of years. 100 million years is only 0.1 billion years, or 1/46 of the age of Earth. So sections of Earth's crust are in rapid motion viewed from the perspective of geologic time scale. Third, most of the geologic features, mountain ranges, the Grand Canyon in US, and even the outline of the continent are relatively recent products of Earth's active surface. Earth's surface is constantly renewed. The oldest known Earth rock, small crystals called zircons from the Western Australia. Okay? And you can see, namely, this one. And they have 4.3 billion years old. Most of the crust is much younger than that. Most of the mountains and valleys you see around you are probably no more than a few tens of millions of years old. Recall from the previous lecture that melting a rock resets its radioactive clock. So those ages always refer to the time span since the material was molten. Okay? When you think about Earth's atmosphere, you should consider 3 questions. How did it form? How has it evolved? And how are humans changing it? Answering these questions will help you understand other planets as well as the Earth. our planet's Earth's atmosphere. Its primary atmosphere was once ruled to have contained gases from the solar nebula, such as the hydrogen and methane. Modern studies, however, indicate that the terrestrial planets formed hot, so gases such as carbon dioxide, nitrogen, and water vapor could have been outgassed from the rock and metal as Earth grew. In addition, the final stages of planet building may have seen Earth and other planets accreting planetesimals, reaching volatile materials such as water, ammonia, which contains nitrogen, right, and carbon dioxide. And thus, the primary atmosphere was probably rich in carbon dioxide, nitrogen, and certainly water vapor, from both outgassing and from planetesimals in part. The atmosphere you breathe today is a secondary atmosphere produced later in Earth's history, partially by further outgassing and by green plants that produce oxygen. Soon after Earth's form, it began to cool. Once it cooled enough, oceans began to form, and carbon dioxide began to dissolve in the water. Carbon dioxide is highly soluble in water, which explains the easy manufacture of carbonated beverages. As the oceans removed carbon dioxide from the atmosphere, the carbon dioxide reacted with compounds dissolved in the water to form silicon dioxide, limestone, and other mineral sediments. And thus, the oceans transferred the carbon dioxide from the atmosphere to the sea floor and made the air correspondingly richer in the other gases left behind, especially nitrogen. And this removal of carbon dioxide is critical to Earth because an atmosphere rich in carbon dioxide can trap heat by a process called the greenhouse effect. When visible wavelength sunlight shines through the glass roof of a greenhouse, here you can see the process like wavelength red arrows, right? It hits the benches and plants inside. The warm interior radiates heat in the form of infrared radiation, which can't get out through the glass. Heat is trapped in the greenhouse, and the temperature climbs until the glass itself grows warm enough to radiate heat away as fast as sunlight effect enters. Of course, a greenhouse also retains its heat because the wall prevents the warm air from mixing with the cooler air outside, right? And this is also called the Parker effect for obvious reasons. Like the glass roof of a greenhouse, a planet's atmosphere can allow sunlight to enter and warm the surface. Carbon dioxide and other greenhouse gases such as water vapor and methane are opaque to infrared radiation. So an atmosphere containing enough greenhouse gases can trap heat and rise the temperature of planet's surface. It is a common misconception that the greenhouse effect is entirely bad. Without the greenhouse effect, Earth would be at least 30 Kelvin colder, with a planet-wide average temperature far below freezing. The problem is that human civilization is rapidly adding greenhouse air gases to those that were already in the atmosphere. For 4 billion years, Earth's oceans and plant life have been absorbing carbon dioxide and burying it in the form of carbonate, such as limestone, and in carbon-rich deposits of coal, oil, and natural gas. In the last century or so, human civilization has begun digging up those fuels, burning them for energy, and releasing the carbon back into the atmosphere as carbon dioxide. And this process is steadily increasing the carbon dioxide concentration in our atmosphere and warming Earth's climate in what is called global warming. Global warming is a critical issue because it will change climate patterns, warming some areas and cooling others, directly affecting agriculture. In addition, global warming is melting the polar ice caps, causing sea levels to rise. A rise of just a few feet floods major land areas where many people live. When you visit Venus, you will see a planet dominated by a runaway greenhouse effect that destroys the planet's original environment. I hope it's enough for now. Okay. Next lecture will be continuing studying the terrestrial planet. And now, I think you enjoyed this lecture, and I'm looking forward to see you next time. Bye.